Hello and welcome to this short presentation on website performance. During this presentation, we'll be taking a look at how to measure performance and metrics which we'll be using on performance, as well as we have some code examples and some quick snippets which you can take from our GitHub repository and apply to your own project with relative ease, but with large gains on the performance. So let's get started. Short introduction about myself. I am Kevin Farrugia. I'm a co-founder at Incredible Web, a software development company based in Malta, and we develop a wide variety of software applications, ranging from websites, mobile applications, to more complex artificial intelligence applications. And over the past 2 years, we have been actively involved in progressive web applications, or PWAs, and this has pushed me to investigate and to research more on website performance, as this is one of the prerequisites for a top-performing PWA. But why does performance matter? So performance has been proven by Google and other reputable sources that it affects the bottom line. So it affects your conversions. A website which performs slowly either will see users leave the site before they are able to see the content or before they are able to convert, or they will not finalize if there's a checkout process, for example, they might not finalize the checkout process because of performance issues. But what is fast? Originally, when we're talking about website performance, the most popular metric would be the time to first byte. So how long it takes until you send a request to the server and the server responds with the first byte, which will be the document which you're going to parse. There's also the document ready and the load events, and these are similar metrics when your document or when the HTML is visible or has been downloaded onto the browser. However, recently, since 2016, Google have coined the term time to first meaningful paint, and this is the time it takes until the screen or the viewport, for example, if you're looking at your mobile, the viewport is painted, or most of the layouts have been painted. And this is going to be our primary metric for website performance. And the difference is that now we're evolving towards human-centric metrics. So metrics which will improve the user performance. So ultimately, the user is going to have a better experience if you improve the website performance. Additionally, there's also the time to interactive. So this is how long it takes until the main thread is able to handle user input. So once you click on, like, let's say, a text box and you start typing, how long it takes until you are able to click on the text box and that event is being handled. And time to consistently interactive is when the main thread is idle, so it is able to, it's not busy, so it returns every 50 milliseconds, it returns control. Jank-free is another human-centric metric. It is related more towards the user interaction. So, for example, when you're scrolling, it isn't lagging, or when there are some animations, they are smooth. And the key would be to always interact and have everything at 60 frames per second. What we're seeing is that load or performance is no longer about just initial load time. Performance is an experience from the beginning of a user navigating to your site and till the end. So even the interactions with the site, the animations on the site, and even how you show, so perceived performance, how you're able to show the user, hey, this is loading. Once the content has loaded, we're going to show it to you. And this is the rail model, also coined by the Google team. For the scope of this presentation, we're going to be looking at or using two tools mainly. So the first one on the left is Lighthouse. It is included on Chrome DevTools by default, or CLI. And the one on the right is also from DevTools. It is the Flamechart, so the performance tab inside your Google DevTools. For the scope of this demo, we're throttling our connection to a fast 3G, and our CPU has a 4x slowdown. So this is our baseline. It is a simple application. It looks like this. We're using the App Shell model. Very simple website. Of course, it is better to run your performance on real-world scenarios, but since we have a very short time frame for this presentation, I said let's do something very simple where it is very easy for you to understand and very easy to take these bits and pieces of code and add them onto your own. In fact, if you take a look at the code, which is available on GitHub, the links are in the description below. If you take a look at the code on the master branch, so the master branch is the original starting point, our baseline. And if you take a look at it, it is a simple HTML page, nothing fancy. We've got our head. Inside our head, we've got a link to our style sheet. This is the traditional way of loading style sheets. And in the footer, we're loading scripts using the async tag. In the beginning, I mean a while back, the scripts also used to be loaded in the head, again delaying the load time or the time to first meaningful paint. What we'll do, we're going to take this baseline and we're going to do improvements and iterations on it so that we improve our performance. But for a start, we'll have to take a look at our current performance, and this is what it looks like from Google Lighthouse. So if we take a look at our first meaningful paint, it is taking 2.5 seconds, which is decent, but obviously remember this website is relatively simple. And as you can see from the timeline, time to first meaningful paint occurs when we've got the content, so on the page. So we've got the header, the title, and the HTML text. The image is still being loaded and was excluded for the scope of first meaningful paint. First interactive and consistently interactive are at 3.6 seconds, and they are identical because there isn't a lot of JavaScript occurring on this page. If we take a look at our Flamechart, I won't go into much detail, but the Flamechart itself is divided into different sections. So the top section is like a timeline and an overview. You've got also some screenshots to help you. The section which we've got open over here is the network section. So we are able to see network requests, how long they are taking, and the order in which they are occurring. And below, we've got the main thread, how long the main thread is taking, and on what it is spending its time. And this is most likely going to be JavaScript and evaluation of JavaScript, etc. So the first improvement we're going to do is going to inline critical CSS. So what happens when you load a website, the first request, it's going to be a get request for the document, and this is going to include the HTML, which will build the page. And HTML can be parsed incrementally. So whilst the HTML is still being downloaded, it can already start being parsed by the browser. Unfortunately, CSS is non-incremental and render blocking. So the page is not going to be rendered until the CSS has been downloaded. And the reason being is that how it works, the browser, so you've got the DOM and you've got the CSS object model, and it combines the two to create a render tree, and then it will use this render tree to paint to the screen. Until the CSS has been downloaded, of course, we are unable to build this render tree. So what we're going to do, we're going to inline our critical CSS. So this is the CSS, the minimum amount of CSS needed to render the above the fold content. So our time to first, what is showing in our time to first meaningful paint. And it will look something like this, the output HTML, which is obviously against all practices which we have learned. So separation of concerns, we've got our CSS inside our HTML. Having said that, we're able to use some tools. In the demo, we're also using some tools built in Node.js, which allow us to separate our files. So as a developer, it is not going to look like this. It is just the output file. And we're still able to work on our CSS separately. And then the inline CSS is injected automatically and minified and placed into the head of your HTML. By doing this small improvement, we'll take a look at our Lighthouse, and we can see that the first meaningful paint has jumped down or fallen down to 2 seconds now. So we're saving 500 milliseconds almost. And time to interactive and consistently interactive have remained the same. If we take a look at our network tab, our network section inside the performance tab on DevTools, we will see that the style.css is loaded afterwards. It is loaded after the time to first meaningful paint, and this is because how we have set up our page, the changes which we have done. What we have done is that the inline CSS is being loaded as part of the head. Everything else is being loaded asynchronously. So in this case, style.css, which is the CSS needed for the remainder of the website, or anything below the fold, that is loaded asynchronously and later. And this is obviously not going to affect our time to first meaningful paint, as it won't affect anything rendering above the fold. There are a number of plugins to do this. There's the load CSS from Filament Group recommended. In this example, we're using our own implementation, which is also relatively simple. The next improvement which we're going to look at is to take a look at our critical request chain and see what can be improved over there. So the critical request chain are the requests or the items needed for the time to first meaningful paint, and these can be extracted through Lighthouse once again. And what you will notice if you take a look at your critical request chain is that font files are a requirement for the first meaningful paint, but they are only requested after the render tree is constructed. And this is because the browser is clever, and it will see that if there are font files which are not going to be used as part of the CSS and HTML that you have downloaded, so there's not going to be the requirement for a font file, then it will not download this. And this is a feature that the browser has inbuilt into it. On the downside, this means that to download these font files, we need to wait until the render tree is parsed. So what we can do, if we know that there are font files which are definitely going to be used on our page, we can preload our web fonts. There are two main ways how to preload web fonts. You could either add the preload tag to your HTML. My preferred implementation is using server-side headers, which in this example are being added using Express.js. And it looks something like this. So it's a very little snippet of code, but it is enough to drastically improve your performance. As you can see, our first meaningful paint has now fallen down to 1.1 seconds, sorry, and interactive and consistently interactive have remained the same. But if we take a look at our Flamechart, we will see that the fonts, which were before occupying quite a large chunk of network download time, are no longer visible as they are preloaded before. The third and final implementation, which we'll look at, is code splitting. So something important to note is that 100 kilobytes of image are not equivalent to 100 kilobytes of JavaScript. After the JavaScript is downloaded, it needs to be parsed, it needs to be evaluated. You can see this inside the main thread, inside the performance tab, and it needs to eventually run. So there are two implementations which can improve your JavaScript parse time, let's say. And these are tree shaking and code splitting. So tree shaking is a concept, for example, it is built into Webpack, and it is a concept of removing modules which you are not going to be using as part. So we've got some modules included in your code. They are not imported. If we're using ES6 imports or similar, they are not imported, so they will not be included in the resultant output file. Code splitting is the concept, which is the one which we will take a look at during this presentation, is the concept where you will get your file, your JavaScript file, and split it into a number of different files depending on the page. So for example, if you're on the home page, you don't want to download this one giant JavaScript file for the whole site. You just need to download the JavaScript which is going to be used on the home page, or perhaps even smaller, what is going to be used above the fold. If we take a look at using, in this example, Webpack Bundle Analyzer, which is a tool which creates this map of your JavaScript dependencies and modules, we will see that we have a single JavaScript file, index.js. Inside it, we've got some content or some modules coming from Node modules, Lodash, which is massive and occupying a large part of our JavaScript file, and Axios library, which is used for requesting content from an API. And on the right, the thin section, that is our own code, which we need for our own homepage. So that is our implementation. For the scope of this example, Lodash is being imported as an entire module, whilst it is possible to import only the modules you are using. So let's say, for example, you're going to be using the for each module from Lodash, you can import just the for each without having to import the entire Lodash library. This allows you to make your Lodash dependency much smaller. In regards to code splitting, we're going to be using the CommonsChunkPlugin inside Webpack, and this is set up, as we can see in this little code snippet on the left. And what we are doing, we are creating the index.js, which is going to be downloaded on the home page, and the JavaScript, which is going to be needed on the other module, will be placed. So another page, for example, is going to be placed in a separate entry, a separate JavaScript file called other-module.js. And finally, in the plugin section, we're also using the CommonsChunkPlugin. And what we're saying is that if there is JavaScript module which is being used in 2 or more entries, so in 2 or more files, then place it inside common.js so that it does not have to be downloaded on each or included inside each module. The resultant Webpack bundle analyzer would be something like this, where we've got our module, other-module.js, which is down, including Lodash, as that is one of its dependencies, whilst the homepage did not require Lodash. On the right, you will see the common.js, which includes Axios library, because this was being used by both other-module and index.js. And finally, this little blue section in the bottom right, that is the index.js, which is the code which will download on our homepage. We will run one Lighthouse one last time, and we can see that we managed to push down our first interactive significantly now. So first meaningful paint is at 1 second. First interactive is just over 1 second, and consistently interactive is still the same as first interactive. And if we take a look at our Lighthouse score, we managed to reach 100, which is a perfect score. And well, that's it from my end. Thank you for listening. If you have any queries, just get in touch by email, GitHub, or whatever you prefer. As I said, links are in the description. And thank you very much.